The project we will be doing is based off of a greenhouse built by a retired post office worker in Nebraska. Russ Finch became famous for implementing greenhouses that use ground heating to produce lemons, oranges, and grapefruit throughout the year. Mr. Finch uses approximately 600 feet of piping, buried about 10 feet deep, to keep his greenhouse model at a consistent temperature. The purpose of our project is to model why this is effective, to optimize his design, as well as to analyze the limits of effectiveness of the surrounding soil.
For designing our greenhouse model, several things had to be taken into consideration, such as how much the environment affects the actual greenhouse conditions. So in order to make our model work, the assumptions we made were for the size of the greenhouse, the average environmental conditions, and the material properties of the greenhouse. For the size of the greenhouse, what was chosen was the industry standard for vine or fruit-bearing vines in a greenhouse, and this was about roughly 90 feet long and about 30 feet wide and about 12 feet tall. And so the average environmental conditions that we chose were actually from Rexburg through the months of September and March, and these included such things such as average wind speed, the average amount of sunlight that was given. This was about 65% sunlight on an average day during those months, and the wind speed was roughly 2 meters a second, and the average temperature during these months is usually around -4 degrees Celsius. All the calculations for the energy balance were done in metric. And for the material of the greenhouse, we used polycarbonate because that's really standard for a lot of sturdy built greenhouses. The one shown in the picture uses more of a plastic tarp typically, but for our greenhouse we used polycarbonate. So in order to grow oranges in our greenhouse, an energy balance was done on it to determine the mass flow rate that we would need from the ground heating pipe to maintain an atmosphere within the greenhouse that would allow the oranges to grow. So the energy balance that was done found that our variables were going to be energy into the greenhouse, energy out of the greenhouse, and storage through the pipe flow in the greenhouse from the heated pipes underground. The radiation was from the sun, atmosphere, and ground temperatures.
The first thing to consider in using ground heating is how warm is the ground and how deep do the pipes need to be. By gathering the mean annual temperature in a location, the mean temperature underground will be the same, which in Rexburg is around 49 degrees Fahrenheit. The fluctuation of the ground temperature will vary depending on the depth, as can be seen in the image to the right. Since we will be burying the pipe around 12 feet, our fluctuations will be around 3 degrees Fahrenheit. To determine the length of the pipe, the equation on the bottom left was used, with T infinity being the ground temperature. By substituting UA using the total resistances, we can solve for the length of the pipe necessary to produce the desired output temperature of 45 degrees Fahrenheit using a chosen input temperature of 35 degrees Fahrenheit to protect our precious oranges. The resulting length is 18 meters or 58 feet of pipe. Now that we have our length, how long will that length be effective? Since the heat is transferring through the soil over time, it is necessary to use a multidimensional transient conduction model to get an idea of how long it is effective. The basic idea of this is to take the product of two one-dimensional solutions. In our case, we will take the product of the semi-infinite solid and the infinite cylinder, as can be seen in the top equation. This solution for the semi-infinite solid is the middle left equation, and for the infinite cylinder, the middle center equation. Because we are not interested in the temperature at the center line, a second product must be made between that of the center line of the infinite cylinder and of the radius desired. The results are multiplied and the temperatures at a certain time and at a certain location can be achieved. For the greenhouse, in our situation, the results are displayed. Given the black poly pipe size of 15 centimeters, a location of 2 meters down the pipe, a radius of 10 centimeters outside of the pipe, the plot on the left shows the temperature with respect to time. The vertical line shows the minimum desired temperature. The results are around 2.7 million seconds, which is around 30 days. It can therefore be determined that it will be necessary to have 6 lengths of 18 meters of pipe to last the entire winter of 6 months, assuming the conditions that we have described. To better understand the heat transfer through the soil and the pipe, an experiment was executed. A half-inch PVC pipe was buried in a 12 by 6 by 6 inch box and filled with what we would consider standard soil. Thermocouples were placed 5 centimeters and 10 centimeters down the pipe from the opening and 2 centimeters and 4 centimeters away from the outer diameter of the pipe. Thermocouples were placed in the openings and exits, as well as the velocity was recorded for calculation purposes. A heat gun was placed at the entrance and the experiment went underway. Predictions were made that at the first thermocouple, that after 480 seconds, the temperature would be approximately 13.2 degrees Celsius, and that the actual temperature was 13.8 degrees Celsius after we measured it. It's only a 5% air, so not too bad. With the inlet temperature being 147 degrees Celsius and the outlet being 121 Celsius, the data is displayed with 2 cycles performed to observe the cooling and heating effects. The data from our experiment shows that the relationship between the change in temperature with respect to time is a constant relationship regardless of the distance on the pipe, while the thermocouple at 5 centimeters down the pipe and 2 centimeters away from the radius and 10 centimeters down the pipe and 2 centimeters away from the radius are different temperatures. This is because the steady state temperature in the pipe at that location is different, but the rate at which they increase share a very similar pattern. This is also seen in the 10 centimeters down the pipe, 4 centimeters out, 5 centimeters down the pipe, and 4 centimeters out. The larger radial distances from the pipe. This is informative to know, since it affirms that the entire pipe will become ineffective equally after a time period and not just in the first several feet. While this project was limited and much of the material is far more complex than an undergraduate degree can cover, it was found to be entirely feasible to grow oranges in Rexburg using a ground-heated system.